Good morning. This is Jinil, and I'm going to present on the optional assignment one. The problem that I'm going to discuss is about the longest common substring problem. So, in this problem, you are given a string of t and characters from a constant size alphabet. We want to find the longest substring of t appearing at least twice. So, a dynamic programming solution already exists for this problem, but we are going to discuss about a faster solution, that is linear time using suffix array and the LCP array. So I'll be discussing about our approach to achieving a linear time solution. First, let's talk about our goal. We aim to efficiently find the longest repeating substring in a given string. To achieve this, we'll adopt a linear time solution. Our approach involves the following steps. First step is the suffix array construction. We start by taking all suffixes of the given string and sorting them lexicographically. We define a suffix array SA where SA of k equals to x denotes the kth smallest suffix in order. And the second step involves the longest common prefix array computation. Once we have our sorted suffix array, we compute the LCP array. LCP array represents the length of the longest common prefix between consecutive suffixes. It's computed using a linear time algorithm such as Kasai's algorithm. Finally, if we find the maximum value in the LCP array, this maximum value represents the length of the longest repeating substring in the given string. So now let's discuss the advantages of our problem. So by utilizing the sorted suffix array, we streamline the computation process, leading to improved efficiency. We compute the LCP for consecutive suffixes in a linear time manner, reducing overall time complexity. So in terms of implementation, I already discussed that we are going to construct a suffix array in linear time, and for that we are going to be using DC-3 algorithm. And for computing LCP array using linear time algorithm, we are using Kasai algorithm. Then at the end, find the maximum value in the LCP array and then solve the problem. So yeah, first I'm going to talk about the DC-3 algorithm. So the DC-3 algorithms involves the following steps. So the first step is constructing the sample. So we consider a string t and we divide the indices of the strings into three sets based on the remainder. So it divided by 3. So B0 contains indices 0, 3, 6, 9, 12 according to the string t, and B1 contains indices 1, 4, 7, 10. B2 contains indices 2, 5, 8, 11. Then further we create a set by combining B1 and B2, which represents the indices of the sample suffixes. And the second step in the DC-3 algorithms involves constructing R to sort sample suffixes. So we create substrings R1 and R2 by grouping characters of T based on their positions modulo 3. R1 consists of group characters starting from position 1, 4, 7, 10, etc. R2 consists of group characters starting from positions 2, 5, 8, 11, and etc. Then we concatenate R1 and R2 to form the string R. This step is very crucial for sorting the sample suffixes. So the step 3 involves sorting the characters of R. So radic sort is applied to the characters of R to obtain a new string R0, which involves sorting the triples within R. And the step 4 involves sort the suffixes of R0 if needed. If any characters in R0 are identical, we recursively sort their corresponding suffixes. This step establishes a relationship between the sorted order of R0 and the suffixes of the original string T. And step 5, we use sorted order of R0 to sort sample suffixes of T. By combining the results from previous steps, we assign ranks to each suffix in the essay. So the step 6 of the DC-3 algorithms involves sorting the non-sample suffixes. We handle the non-sample suffixes, which are the suffixes with start indices in B0. We represent each of these suffixes as a tuple combining the starting character and the rank of the next suffix. We compare these tuples to determine their orders, and then finally we radic sort the tuples to obtain the ordering of the non-sample suffixes. The step 7 is the merging step. So we merge the two sorted sets of suffixes, sample and non-sample, using standard comparison-based merging techniques. To compare a suffix from B1 or B2 with a suffix from B0, we compare the respective tuples. This merging step finalizes the construction of the suffix array. This is how the DC-3 algorithms helps us in construction of the suffix array in linear time. So now I'll be discussing about the Kasai's algorithm, which is a crucial method for computing the longest common prefix array, that is the LCP array from the suffix array. This algorithm plays a significant role in various string processing tasks like pattern matching, text compression, and bioinformatics. So yeah, so now let's talk about the algorithm overview of Kasai. So for each index I in the range 0 to n minus 1, where n is the length of the string, we compute the pair ij, where j equals to sa of minus 1 I plus 1. Next, we compare the suffixes starting at I and j to determine the length of the common prefix. We then record the length of the common prefix in the LCP array. For the time complexity analysis, the Kasai's algorithm operates in linear time, that is O of n. Initially, we set k equal to 0 and it is reset to 0 when sa of minus 1 of I equals to n minus 1. For each new index, ik is decreased by 1 and can increase at most 3n times. Every time there is a mismatch, I advances and k increases. Thus, the overall time complexity of the algorithm is O of n. This algorithm's linear time complexity makes it highly efficient for processing large strings and is widely used in various applications requiring the computation of the LCP array. Now I'll be discussing about the claim related to Kasai's algorithm, which states that suppose I0 and J0 are two consecutive elements of the suffix array, let k equal to LCP of I0, J0. If I equal to I dash plus 1 and j is the successor of I in the suffix array, then LCP of I, j is always greater than equal to k minus 1. So now let's walk through the proof step by step. So first we'll be handling the best case. If k less than 1, then the statement is always true. So let's consider the case where k is greater than 1. So we know that suffix starting at I naught is less than the suffix starting at j naught and they have a prefix of length k greater than 1 in common. So now let's consider the suffix starting at I equal to I naught plus 1 and the suffix starting at j naught plus 1. These two suffixes have k minus 1 greater than equal to 1 characters in common. So now we will deal with different successor. If j equal to j naught plus 1, then the proof is straightforward. However, if j not equal to j naught plus 1, we observe the following. Suffix of I is less than suffix of j is less than suffix of j naught plus 1. Since suffix of I and suffix of j naught plus 1 have a common k minus 1 character prefix, it follows that suffix of I and suffix of j have at least that many characters in common. In summary, regardless of whether j is the immediate successor of I or not, the proof holds true. So we talked about both the algorithms, the DC-3 and Kasai. So together, these two algorithms offer a powerful solution to the problem, achieving a linear time complexity and enabling the efficient identification of the longest repeating substring in a given string. Thank you.